So it's a simple problem, and the answer is the gravity of the stars is not enough to hold the clusters together. Off by a factor of 50. Not even close. And so Zwicky did kind of a Sherlock Holmes thing, which is, when you've eliminated the possible, the remaining hypothesis, no matter, the quote, I can't remember my quotes here, no matter how crazy, must be true. So he posited clusters must be held together by the gravity of unseen dark matter. So we can't see it, but it's there. How do we know it's there? Because of its gravity. That's simple. Very simple hypothesis. Simple doesn't mean right, but very simple hypothesis. And so here's the Chandra X-ray Observatory. Did I tell you it was named after a University of Chicago scientist? Just checking. This was in observations starting to be made in the 1980s, looked at clusters in the X-ray, and they looked like this. They were purple. Okay, so that's a false color picture. So it just means there were a lot of X-rays coming from clusters like Coma. But do you see any galaxies in that picture? Maybe one or two. But let me remind you what Coma looks like. So there's stuff in between the galaxies, really hot gas that gives off X-rays. And what's interesting about this is, first of all, dark is a relative term. So dark meant you can't see it with your eyes, but we can see it with X-ray eyes. And it turns out most of the atoms in a cluster of galaxies are not in the stars, but are in the hot gas. So I bet you're all sitting on the edge of your seats wondering if the hot gas is the dark matter. But you already know it isn't, but I'll tell you that. So lots of hot X-ray gas. Stars are only the tip of the iceberg. So most of the atoms in the universe, we won't come back to this, but most of the atoms in the universe are dark. So stars only account for 0.5% of the universe. But there's not enough mass in the hot gas to hold clusters together. Still off by a factor of 7. Okay. When in my early years at Chicago, I had a provost who was a lawyer, and they have very logical minds, and they're very rigorous. And so I was trying to explain dark matter, and this is the picture that convinced my lawyer provost that there's dark matter. So this is a cluster of galaxies. Its phone number is 0024 plus 1656. Do not call that phone number. It's a toll call. It's not. And the cluster galaxies are orange. And then let me do the setup here. So these blue things, these faint blue things, are called faint blue galaxies. And those are galaxies far behind the cluster. And so their light has had to come to us by passing through the cluster. And these faint blue galaxies look very weird. Look at that. That one's stretched. Look at that circular one. In fact, there's 5 circular ones. What's going on here? Well, what's happened is that Einstein told us that gravity bends light. The gravity of the dark matter is bending the light. Light bending, that's what lenses do. And so the cluster is acting as a gravitational lens, and it's, in this case, making multiple images of the same galaxy. When you get further away, it shears the galaxy. It's not really like a cigar. The image got sheared. And because we know how gravity bends light, we can actually then reconstruct what is the mass distribution in that cluster. And these are the 2 directions on the sky, and this is mass. And these are the technique is so powerful it picks out the individual galaxies. So you ask me, where's the dark matter? Well, the dark matter is the smooth component. So the dark matter is really there. Actually, in the reception, you can make your own gravitational lens. What you want to do is take the wine glass and break the top off. Mark, that's okay, right? They can do that. And then the bottom will serve as a gravitational lens. Or you can do it at home. Maybe they should do it at home. Okay. The next part, timing is everything in science. So when Zwicky was telling people about dark matter, cosmology was very, very young. And every time you looked on the sky, you saw something interesting. And so the dark matter problem didn't get paid much attention to. Some people said, hey, how do we know clusters even exist? Maybe they're just chance, ships passing in the night. The person who brought the problem closer to home was Vera Rubin. Another interesting story here. Vera Rubin got her PhD. She was supervised by George Gamow. Why was she supervised by George Gamow? Because very few astronomers would supervise a woman. And in fact, she had an interesting experience at Princeton. She tried to apply to Princeton, but they wouldn't even send her a catalog. And they noted her interest in art and in astronomy and thought that a career in painting astronomical objects might be a good one for her. And so Vera went to George Washington University, and George Gamow was her mentor. And she discovered that dark matter is everywhere, and you don't have to go to clusters. So this is, this in fact is Andromeda. And I'm going to talk about this plot here, but again, for those of you who get scared with plots, think of Monet paintings. So what I'm going to plot here is how, in a galaxy, stars move around the center. And this plot just tells you how fast the stars at a given distance from the center are moving. And so what she discovered is flat rotation curves. And let's pretend that all the mass of a galaxy were associated with the stars. It isn't, but let's pretend. Then, as you got farther and farther away from the galaxy, gravity is getting weaker and weaker, and the stars better be moving slower and slower, otherwise gravity is not going to be able to keep them in their orbits. And so something's wrong here. The rotation curve, if all the mass were associated with, if the stars were the only thing there, you would see a rotation curve that goes down like that. And so thousands of rotation curves have been measured since she did her pioneering work. And, oh, there it is, blown up. It's the same curve. Andromeda must be embedded in a dark halo, and I'll show you a picture of that. So the fact that you have the velocities that stars very far from the center are moving as fast as ones closer to the center means there must be some more material. So here is a picture of our own Milky Way galaxy. How can you take that picture? That's because we're not at the center. How many have been to Chicago? So you go out on the lake, right, and you look at the skyline and you can take a picture, a panorama picture. So this is the same thing. We're not downtown in Chicago. We're out here in Charlottesville. And so this is what the galaxy looks like in light. So that's the bulge, and it's infrared light, and that's why you don't see all the dust. And here's what it looks like, the artist rendition. I apologize. This is what the dark halo looks like. And actually, it's not what the dark halo looks like. The dark halo is much bigger. So this is 100,000 light years across. Our dark halo goes all the way to Andromeda. So a million light years. So these things are enormous. We are just the nugget at the center. Okay, so what is it? So everywhere you go, there's evidence for dark matter. What is it? So this is such a fun game that's been played over the years by astronomers, and I apologize for going through it quickly and not, letting audience participation. Black holes, no. So we have a big black hole at the center of our galaxy, but it accounts for less than 1/millionth of the mass of the galaxy. I told you last time that a black hole is born every 10 seconds. Again, the math doesn't work. Well, I guess if you're running for president, the math doesn't work. White dwarfs, no. Faint stars, no. Greenhouse gas, no. Dust is an easy one. So I can show you the reasoning. If the dark matter in our halo were all dust, we couldn't see anything. That's how much dust you'd need. Okay, none of the above. So now we're going to do more math. Okay, but this is really simple math. So we have an accounting problem. So we know how many atoms there are in the universe. that totals up to 4% of that, what is called the critical density, to get the Goldilocks universe. We know how much matter there is. The total amount of matter adds up to 28%. Okay, so does anyone here think 28 is equal to 4? Okay, good. Does anyone think 4 is greater than 28? No. How many people think 28 is bigger than 4? Okay, so you see the math problem. And I'll tell you how we know how many atoms there are in the universe. But here's the math problem. There's not enough atoms in the universe to be the dark matter. So we go back to Sherlock Holmes, and the simple deduction is we've eliminated the impossible. And so whatever remains, however improbable, must be correct. Oh, I think I said it right. So the dark matter is a new form of matter. Okay. So what is it? So this is what came from collaborating with those particle physicists. It turns out those pesky little particle physicists, in making their grand unified theories, these theories that unified all the forces of nature, predicted the existence of new particles. And they predicted them for their own purposes, but it turns out that when the cosmologists, like me, got a hold of them and asked how many would be left over from the quark soup, guess what the answer is? About the right amount to be the dark matter. And so, let's see, I'll start here with the neutrinos. There are 3 kinds of neutrinos, and this is what we love. You get 3 tries. And we know there's neutrino. The neutrino has the virtue that it actually exists. Everybody's heard of the neutrino. Even John Updike knows there's neutrinos. So if anybody read Cosmic Ball, it's a great poem. The only issue with the neutrinos is what is their mass. And over the last few years, particle physicists have zeroed in on the mass. It's a really exciting story. They don't quite have the mass yet. But we now know that neutrinos only contribute a few tenths of a percent. And the big question with neutrinos is, will they beat stars? So they're nowhere near the 28, but they might beat stars, and there might be more neutrinos than there are stars in terms of mass. I'll talk about 2 particles here, mainly one, because everybody's heard superstrings. So the superstring theory is a wonderful theory. It's a very extravagant theory. It predicts extra dimensions where you can have offshore banking accounts. So I guess a number of people did watch Page-Barbour last night. And it also predicts that for every known particle, there's a new particle called the superpartner, the supersymmetric partner. And of course, these string theorists, they're so creative. So they think that because half the particles in their theory have been discovered, that's real progress. Of course, all the new ones predicted haven't been discovered. But anyway, the lightest of these new particles has a goofy name, the neutralino. It'll get changed if it really turns out to be the dark matter. And there's enough neutralinos left over from the Big Bang to be the dark matter. And so the neutralino is an example. Let me tell you a little more about it. It weighs maybe 100, maybe 500 times what the proton does. If they really exist, then in every coffee cup that you carry around, there's one neutralino, which is why the coffee spills. They're very shy. They're very shy. They interact like neutrinos do. Anyway, this is an idea from particle physics. The axion is my favorite, and I'll come back to it next time. But that's another possibility.